So when we're working with things like this for our bell work, we're just going to start doing some substitution. We're picking x values. They've picked some for us here to start. We can always use a little more if we need to get a good idea of what's happening. But mostly what we're going to do is we're going to take these and we're just going to substitute them in, typing them into the calculator, being very careful. What value do we get when we substitute in -2? -2. It spits right back out at -2. What do we get when we substitute in -1? -3. How about for 0? +2. What do we get for 1? 25. And for 2? 78. So we can plot this up with the information that we have here. We've got our -2, -2, which is a point down here. -1, -3, which is down here. 0, 2 is way up there. 125, and we are officially off the graph. 278 is even further. So from the table I have here, I don't really know what's going on the left. So let's think about our end behavior here. Is this polynomial even or odd? Odd. So are my arrows going to point in the same direction or the opposite directions? Opposite directions. Which way is my right arrow going to go? Up. We know that because our leading coefficient. It's positive. I mean, we can also see that 278 and 125 are like, way up. So my left arrow is going to point which way? Down. And you can, if you want to, be like, all right, I'd like to know a little bit more, and you could put -3 in to get something going on over there. It is going to, in fact, be more negative. Over here. So this is all we need to get our sketch here. So we're going to pick one side to start at, connect them up. Kind of like that. So where do we have a 0? Yes, a 0, a solution, a root. Negative something, yeah.
Wait, how is it odd?
Because our power is odd. The degree is how we know whether it's even or odd. The leading coefficient is how we tell if it's positive or negative.
Sure.
So odd goes in opposite directions. If our biggest power is an odd number, opposite arrows. Between what two x values do we have a root? Between -1 and 0. Boop, right here. This is where it switched from negative to positive. So this is a solution right there. What kind of extrema do we have here? Say it a little bit louder, I couldn't hear. We have a minimum near what? I was like, we list off the x. So -3 is a part of it, but that is this guy. So we have a minimum. Is this a absolute minimum or a relative minimum? That is the absolute lowest it ever goes, ever?
Oh,
Relative. It's a low point, absolutely. It is a valley, definitely. But it does go lower. So this is a relative minimum. It's the lowest of any of its neighbors. And we'd say that would be near x equals -1. It would be how we list that. A relative minimum near -1. So do we have any other extrema? We have a relative max where? Near -2. So we'll have a relative maximum over here near x equals -2. So that one, our max. Okay. I know I didn't ask you guys to find extrema or solutions, but I'm just kind of using it as a little slapdash review of those concepts. Oh snap, what? Okay. Questions on this? Or on this one? Okay. Because I want to do one more kind of like this from our workbook, just to kind of practice one of the kind of weird ones that we have every now and then. And that would be the ones that look like this. So we're going to look on page 9. We're going to do number 3, and then we'll move on to other things today. I just wanted to do one more of these graphs with our vaguely real-worldy situations, which means a lot of times we don't look at the whole graph, we just look at a part of it. So what we're going to do here is exactly the same as what we did in the bell work. We are going to have an equation here. We're going to try and find all these points. We're going to see if we can find any extrema. And we're going to do what we can. But we're given a whole lot more information, and our equation is a little bit decimalier. So we just got to be careful. Thank you, Dave. So we just got to be careful. We've got our story here. Read through this for a second. Blink. There we go. So the number of quarters produced by the U.S. Mint is approximated by this. So they make a whole bunch of quarters. And they have enough information that they have tabulated that data and found polynomials with it. That is a thing that the data scientists do. Sometimes for fun, sometimes for reasons. But it is what it is. And so X is the number of years since 2005. So our X isn't going to be 2006, 2007, 2008. Our X is the number of years since. So 1 year after 2005 would be 2006. 2 years after 2005 is 2007. So we're going to be counting our X's as 0 being 2005, 1, 2, 3, 4, 5, blah, blah, blah. And then our answer here is the number of quarters produced in millions. So we will get answers that do kind of make sense for those numbers. When we're working with these, we are 100% doing exactly like we did in the bell work, where I'm going to take my information and substitute in X values to try and figure out what's happening with our graph. So we have to pick X values to start with to kind of see where our Y values are going to land before we start numbering too much. We are told that we have a function, so we've got our f of x, that's our y, and we're going to pick some x values. For the most part, we want to start at 0. We should always have 0 somewhere in our table. When we're working with years, we will never go negative because I can't make fewer quarters to go back in time. So we cannot time travel through sheer force of mint. So the smallest number we're going to be able to have on our x's is 0. Then we're going to get a couple more to see what's happening here. We can look at 1, we can look at 2, we can look at 3. I could be real crazy. We could go with a half. I could do in between numbers, but that's being aggressive. So what we're going to do is we're going to substitute those values into our equation just like we did before. Just like we did in the bell work. So see if we can fill in some of this table. Because on these kind of real-worldy problems, we have to come up with a lot of information ourselves. We have to pick our x's. A lot of times we have to number them ourselves. And if you need more data points to get a decent graph, you can always get more points. If you can't tell what's happening, or if we can't tell where things are turning around, pick a couple other numbers. Because we might also want to have, just looking through the numbers, might also want to have something like 7. We might want to have 10. We might want to see what's going on a little further down the road. Usually this will be enough to do it. But sometimes we can get more information. Okay. I'll cover this up because I'd rather have that space to do another point. I'm going to include 7 and 10 in mine. When we're doing these ones that we have to pick our x values, we can count these however we want. I could just count by 1s here. If I want to count by 2s or 4s or 10s, whatever we want to do, totally valid. But we're picking our x values. When we start substituting these in, again, remember you can use that up enter trick to only have to type it in once. What is the value for this function when x is 0? Yeah. When x is 0, our y-intercept is going to be this constant over here, the one that doesn't have any x's. So even with no other information, I could figure out what the 0 rate is, because it's going to be our 3215.4. It's going to be that constant. Every time we're working with one of these, that last number will be what happens when x is 0. What do we get when x is 1? $2,933.4. So we can already see that these numbers are going to be really big. So I definitely do not want to count my y's here by 1s. I probably don't even want to count by hundreds. I might just want to count by like thousands. So I already see that we are at 3,000 and 2,900. So I know for a fact I'm going to have some big numbers here. So if I count this one, you can count by thousands. You could count by 500s if you want to have a little bit more space. I'll probably do by 500s, just because that's going to be easier to see. So once we have a couple of data points, we can figure out how we want to count up on our y's. It is really, 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 really important, and I'm not making this light. It is super duper 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 important. Do not use these numbers on your y. No. Easy to count. Awful. Yes. No. Points we're plotting, count like a ruler. These should always be easy to count, like we're looking at a ruler. Not those. These will go in all kinds of different things. They'll be farther distance apart. Do not use your points to number your y values. Use them to help you figure out how you want these to be. Figure out the vibe of them. Do not use your y values as you're counting on the axis. It will be wrong. I will take points off. I am petty about that one. Do not use your found values as your scale. Fuck me. So find our points, fill in the data, and then we can plot things up to see what's happening here. Because our first point's going to be about there if you counted like I did. And at 1, we're at about 3,000. Because it's 290, or 2,900 is really close to 3,000, so right about there. For when x being 2, we get 2450.8. So we're a little bit south of 2,500. For 3, we should get 1,866. So it's dropping a little bit farther. Around there-ish. 1,800. For we should be at about 1,200, 1,277. Which is going to be there-ish. And if we just did those 4 or those 5 points, it would be really hard to tell what's happening. I know with this having an odd degree, I know we're going to have arrows going in opposite direction. And since my leading coefficient is positive, I know this right arrow is supposed to point up, but I've got no idea where this sucker turns around. So if we can't tell what's happening or how it gets where we need the arrows to be, grab a couple more values to see what's going on. I'm just going to go up. I jumped by 3. So I jumped, okay, maybe from 4 we go to 7, and then we check 10 to see just what's happening a little farther away. So if I substitute in 7, we're actually going to get 472.8. So it's even lower, way down here. But if I put in 10, and I know that's technically off my graph over here, that's okay. We can still get there. We get our 3,176. So it goes boom, right back up. It goes back all the way up to about where it started when we're over at 10, which is just slightly off the edge of our graph. So that gives us a little bit more information that we can see, because this is going to go down like this, and then it's going to come over here and shoot back up. So when we connect this up, using a pen that will actually show up, not white. Our graph's going to wind up looking like that. So when we have these kind of real world situations, like the back of 4.2 has a couple of them, you're going to pick x values. I recommend starting with 0, 1, 2, 3, 4, maybe 5. That should usually be enough to get you there to see where this starts to turn around. Because we want to be able to see what kind of extrema do we have here. We know this is an odd degreed function, so if I was to continue this outwards, it should go down this way at some point. We don't have that information. We're not going backwards in time based off of quarter consumption. But if we had the whole polynomial, it would do this somewhere over here because we have that odd degree. But we're just looking at this portion of it. So what kind of extrema do we have on this portion of the graph? Say it a little louder. We have a relative minimum. We have a relative minimum right about there. So near our lowest point we have on our graph, which is about x equals 7. Now, if you picked a couple of different values, if you picked maybe 6 and 8 to get more points up there so that we could plot things up, You might have a slightly different minimum. We're going to look at that picture that we have as best we can and go from there. Do we have a relative maximum on this graph?
Yes, the top counts.
As I say, this is going out to infinity over here. And this one, I mean, it's the highest of things on this side, but I don't even know what's going on over here. Maybe this graph really just goes up like this for a while more and then would go down. So we can't take an endpoint as a maximum. If it stops there, it stops there. It's not going to count as a relative maximum because it's not the highest of points on either side. It's just the highest of points on one side. It doesn't have a both sides. So this one does not have a relative maximum based off of what we have here. What we do have is a y-intercept. And that y-intercept is one of those things that it's very handy to be able to find. It's our easiest point to get. It's going to be that constant. Constant. That's what I was trying to get. Every time it's going to be that constant. The one that does not have any x's. That 3,215.4 in this case. This first guy, when x equals 0, that's our y-intercept. That is the definition of a y-intercept. Is x equals 0, find y. When we substitute it in 0, we get our 3,215.4. We're going to not worry about the domain and range on this one. It's more important that we just try the graphing part. It's calculatory enough. Because what we're going to do for the rest of today is we're going to not do any more graphing. Yeah. We're going to look at some polynomials. We're going to look on the next page. Questions on this one before I switch to the next page? Because we're going to look at, first things first, if it's a polynomial, and if it's not y, we're going to practice finding our degree. We've done it several times, but we're going to practice it again. And then we're going to try and add some of these things together. So we talked on the very, very first day about what it takes to be a polynomial. We wrote some on page 3. We wrote 2 things that polynomials needed to be or needed to have to be polynomials. The ones we wrote down, we said that it needed to be continuous. So continuous means we're not dividing by x or y, nothing in the denominator, and only whole number exponents. Nothing weird happening on our variables. No roots, no negatives, no nothing. Boring counting numbers only. If I can talk about apples in a bucket using that number, it can be in a polynomial as an exponent. If I cannot use that to talk about an apple in a bucket, I cannot use it in a polynomial. I can have 1 apple in a bucket. I can have 2 apples in a bucket. I cannot have the square root of an apple in a bucket. I cannot have -3 apples in a bucket. That would be that I have a debt of apples in the bucket. That is not cool. You owe me apples? I don't know. So we can't have any roots, negative exponents, or x's or y's in the denominator. So is 1 a polynomial? I was going to say, is this term okay? Is this term okay?
No.
No. Is that term okay? Yeah. Totally fine. So that one's good and that one's good, but this guy's a problem. So because of that cube root, This is not a polynomial. No. If there is one term in a polynomial that does not follow the rules, the whole thing gets kicked out. I have a bucket of mayonnaise right over there, yep. In the first aid bin. What do we think about number 2? Is this one a polynomial? I have only whole numbers as exponents. I don't have anything being divided by x or y. I don't have any square roots on my x's. All of my x's are normal. That's what we need. If we have any weird things on x's, it's a problem. So we are allowed to have exponents, all kinds of things, just they have to be positive, no square roots, cube roots, or anything like that. So this is a polynomial. What is the degree of this polynomial? Say it louder because I heard it right. 7. The biggest exponent is our degree, which makes what our leading coefficient? The 3. So if we were looking at this for our end behavior, those would be the two things we're looking at. My degree is our biggest exponent. The leading coefficient is the number in front of that guy. So that makes this kind of like our boss. That's our boss term. So for number 3 here, what do we think? Polynomial or not a polynomial? No. Because these negative exponents cause problems. What negative exponents do is they put that term in the denominator. This term was the same thing as having 6 over x cubed. It is being divided by x. That's not okay. We can't do that. That makes it non-continuous, which we will look at eventually, just not right now. So negative exponents, if you did that in Algebra 1, it's just been a minute. Negative exponents flip that piece to our denominator. That's why we can't have any negative exponents, because we can't divide by x. It's going to make a problem, because we can't divide by 0 anytime. I'm going to grab a notes packet from there, James. So this is not a polynomial. So I'm going to skip over the next ones real quick. I want us to go down to the adding polynomials, mostly because we've practiced finding our degree several times before. There's going to be times when we are given problems like this and asked to either add or subtract. This guy is a polynomial, 6x cubed plus 7x squared minus 2x plus 5. No roots, no weird negative exponents, nothing else going on. And we're adding this polynomial to it. And again, this is totally a valid polynomial. No roots, no negative exponents, nothing weird going on. If I wanted to add these two polynomials together, what do I need to do? It is 100% combining like terms. These parentheses, since we are adding, these parentheses don't actually do anything for us. This is 100% the same thing as if I had my 6x cubed plus x cubed and my 7, why did I switch to green that one? There we go. And my 7x squared minus 4x squared minus 2x minus 8x plus 5 and plus 1. I can reorder things in whatever order makes sense to me. When we are adding, all we're doing is combining like terms. We do want to wind up in our standard form. That's where we have our biggest exponents in the front. So we're going to do that. Please, please, please remember, we can only combine things together when they have the exact same term. I know these are all very similar. We have x's and everything. But having x's is like having apples. Then x squared, it's not a different flavor of apple, it's an apple tree. Related, similar. Do not hand me an apple tree and say, congratulations on your apple. No, the same thing. And then x cubed, that's an apple pie. Again, do not hand me a tree and say, congratulations, here's a pie. I cannot combine apple pies and apple trees without a whole lot of work to make them be together. So adding and subtracting, totally fine. Apples with apples, trees with trees, pies with pies. Yep. Do not take a tree and a pie and put them together and tell me that's the same thing. So when we're adding these together, we're going to wind up with something that looks like a polynomial. It's going to look like we didn't do much. We're just combining our like terms. Our 6x cubed plus x cubed gives us a 7x cubed. Then we have our 7x squared minus 4x squareds. So 7 apple trees minus 4 apple trees. We get 3x squared, 3 apple trees. Then minus 2 apples minus 8 apples. Minus 2x minus 8x. If I borrow 2 apples and then I borrow 8 apples, how many do I owe you? Minus 10 apples. Again, with negative numbers, whenever it's minuses, feel like it's somebody owing you money. We do a whole lot better with that. 4 apples in this case. And then our last one, we've got 5 plus 1, which is 6. And we stop. That is our answer. I cannot combine x's, x squareds, and x cubes together. They can't do that. That is, again, taking my apple pie, putting a raw apple in the center of it, and says, ta-da, I made another pie. You gotta cook that. There's a whole lot of work to put another apple inside that pie. Do not put a raw apple on a pie and say, that's like I've given you another pie. Nope. Nope. So just be careful with these. Adding these together is very, very much combining like terms. You do not have to write it out like this. This is a way that a lot of times we do it just by combining our like terms together like this. So this was just me kind of drawing these arrows without it getting super duper arrowy. This would be working horizontally on how we can do this. You can also set this up old school column style edition. And I'll show you what I mean by that here in just a second. So let's look at number 2. This will be our last one for today. And again, we're given a couple of polynomials. And we want to add those together. If I want to be able to add this piece, and this piece, I'm going to take this one, my 2x cubed plus 9x squared plus 6x minus 3. And we are going to add, and I'm going to stack them. And I'm going to line up x cubed with x cubes, x squared with x squared, x's with x's. So I've got my 4x cubed here. And my minus 7x squared under the x squared. And my plus 5x over here. And I don't have anything to put under the constant, and that's okay. Because what we're going to do is we're going to add these together column style. Because now I can do it this way where I have my 2x cubed plus 4x cubes, and it groups them together. Huh? It's been a minute. So it's okay to use some of the old tools we've had. Like, this isn't wrong. It totally works. 100% valid, because we still get 6x cubed. Then we have our 9x squared minus 7x squared. Well, 9 trees take away 7 trees, and we get 2x squared, 2 apple trees. And then I've got 6x plus 5x. That's a positive 11x. And then negative 3 plus nothing. Negative 3. So you can either do these horizontally, where I take my 2x cubed plus my 4x cubed and bring it down here to get my 6x cubed. Totally valid. That's what we did on the last one. Or you can stack them and add them in columns. Either way works. We can use either technique. We're going to work more with our operations with polynomials. We'll start doing some subtracting and some multiplying on Monday. So we'll do that. And then I will give you guys 4-3 on Monday just because I don't actually have it copied right now. So I forgot. So work on 4-2. It is due on Monday. And I will have homework 3 for you then. So 4-2 through 11-3.